into science.
Oh yeah, could you tell me more about that?
Yes.
Ty's gonna save you, and I'm coming back to you. Go for it.
He's the atom dude.
Be specific. They're all the atom dudes, and they all are dudes.
Found atoms.
He discovered, and then he made this nice 4-postulate kind of thing, like 4 descriptions. Okay, what did we call that whole thing? Dalton's atomic theory. You guys were just like, it was there, but it wasn't there. Okay. Dalton's atomic theory. How much of that's true today still? Like half of it or less. Okay. He was on the right track, but we can't blame him. He was helping us out. We just had more tools later in the century. Okay, JJ, what did JJ do? Talia, what did JJ do?
He found electrons.
Okay, so his contribution to science is he found the electron. Thank you, internet. And what else? What was his model called? It's yummy.
Oh, plum pudding.
Plum pudding model. Good. Plum pudding. Because he said it's a circle with what's in the inside of the sphere. Dots. So the dots, positive locations or negative locations? Negative. There's like this, and there's a little negative here and a here and a here, and then everything else that's not is positive. Is that what the atom looks like to our knowledge today? No, but thank you for discovering the electron, JJ. We needed that, to get us further. What did Millikan do after JJ? Go for it. Hey. So the mass to charge ratio of an electron. Okay, it just gives us electron has a negative charge, and this is the mass of it. It's very, 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 very tiny. Rutherford's model. Go for it.
He did the gold foil.
Okay, so gold foil experiment, and
He discovered the nucleus.
all right. So he said that he shot he shot what at the atom?
Alpha particles.
Okay, so he shot alpha particles. Remember that? You guys know alpha symbol? I think it's Greek. Is that Greek? Okay, alpha particles. They deflected. He was like, oh no, there must be something big, dense and hard and small in the middle of the atom. So he said that's the nucleus. Okay? Goldstein. Yeah. Okay, to help with the discovery of the nucleus, right? So he helped with the cathode, I'm going to put CRT, cathode ray tube experiments, and he helped modify some of the discoveries of Rutherford and actually JJ too. Chadwick, we're getting down to the nitty-gritty, yeah.
He discovered the neutron.
So the neutron by doing, did he have an experiment?
Not that all of
Hannah's going to add to it, yeah.
it. He shone gamma rays at wax to try to eject the protons.
Okay, so you used gamma rays on some matter to see if he could eject these subatomic particles, and from that he found some mass differences, and then that was how he discovered the neutron is there. It doesn't have a charge, but there's something else there that has mass. So you're apparently Chadwick. Are you Chadwick? Okay, so if you're that person, you actually know a lot more than the basics that I'm putting up here right now. Okay, Bohr. Who wants to tell me about Bohr? Go for it.
He did the electron levels.
Okay, so electron, I'm going to say energy levels. And his model looks like this, right? So he's a lot more detailed. And he said that electrons live in these little neighborhoods around the center of the atom, which is the nucleus. And he said they live either close, which is energy level 1, or farther away, energy level 2 through 6, usually is how far we go, 7 maybe. And these electrons can move from, for example, energy level 1, they can move all the way up to energy level 1, 2, 3, 4, to energy level 4, and then they can drop back down. It's kind of cool. So the electrons can move. And the last one is Schrodinger. Hi, how are you? Yeah, what's up? I do. Feel A. Can you make up that test? Thank you. Okay. So, what does Schrodinger do? Anybody? Anybody? He contributed, go for Aiden, an equation called the wave mechanical model, aka quantum mechanics. Who's heard of quantum mechanics or quantum tunneling or quantum effects? Right, that's really high level physics and chemistry kind of intertwined together, how matter interacts with other matter and how matter interacts with energy. It's really high level. So we're not going to go into extreme detail with him, but we will mention his theory quite a lot. We just won't go into the calculations of it. We'll talk about Einstein and de Broglie tomorrow. Okay. Well, we don't need that. He's a lefty too. Okay, just want to see if that works. Okay. So this is a nice periodic table that Mendeleev kind of set up. What does Mendeleev contribute to the periodic table, or the thought behind it? Mendeleev. Yeah.
He accounted for other elements that weren't found or created yet.
Right. So we hadn't discovered all of them, but he knew that they came in kind of a subset of elements that had similar properties, and he kind of set a periodic table in a row in a period and group like setting. So you can see there's one here. This is my favorite periodic table. Yes, right? My favorite. It doesn't last long though. And then the noble gases are there, nice little like cookies and cream flavor over there. And then my other favorite of the different game characters, so I'm sure hopefully you can recognize at least like one on there. If not, you got to get out more. Okay. Other than that, and then I like to be artsy, so there's different colors. So periodic tables come in many flavors and sizes, but the one we're more concerned about is probably one like you're going to pull out right now that I gave you the first day of school, right? Thank you. If you guys find me a top of our periodic table, let me forever. I can only find it on images from Google. I can't actually find it. I don't know where it is.
We get an automatic
An A in my heart, yes. A in my heart. A with me. Okay, also pull out your notes. There's a big isotope table. We're going to fill that out momentarily. So the back of you yesterday, then it equals a chart. Okay, so let's get the basics of the subatomic particles out of the way, and then we'll apply them, and then we'll apply them hands-on in the lab. Okay, so here we go. This is the shortest period that we've ever had. We usually have like almost 2 hours. We chopped it down, so you got to work with me here. Whenever we talk about subatomic particles, we know they come in 3 different, or there are 3 of them. There's actually more called quarks and stuff, but that's past that. That's above my pay level, okay? So we're at subatomic particles: protons, neutrons, and electrons. You know that protons are going to be indicated on the periodic table in a certain way. So if I draw a little box, and this was on your notes that you guys took by yourselves about the periodic table when we did the chromatography lab, when you look at the little box where carbon is on the periodic table, what's right below it? Below carbon? Like right below the C, I'm sorry.
Carbon.
So it says carbon? Sorry. What is right? Oh, right below that. 12.01, okay. What's in the upper corner? I'm sorry, it's right above it actually. 6, okay. So this 6 right here is the atomic number, okay? That 6 also indicates the number of protons. Yes, we know this now. It's a fact you have to know. There's no, like, way to remember it. It's like you guys got to know it. Like 2 + 2 is 4. You just know it now. Okay, so electrons are not given to you specifically on this little picture from the periodic table. They are assumed to be the same as the number of protons if the substance is neutral. Okay? Neutral means equal protons and equal electrons. So that is true only if it's just written as like just straight carbon, just like that. So if I wrote magnesium has how many protons? Okay? How do you know that? Because it's what? Atomic number. And then how many electrons would it have if I wrote it like that? Say again? 12. There's no way to look at it and tell, because if it's neutral, you just assume protons and electrons are equal. Okay? I think I said electrons, and hopefully I didn't say protons. I mean neutrons. Okay. So that's a neutral atom. If I had an ion, I have 2 ways to recognize ions. They're either positively charged, and they're called cations, or they're negatively charged, and they're called anions. Doesn't anion just sound negative? She's such an anion. Cations just sound like, a cat. I mean, there's a positive charge there, essentially, and it's a T, but it looks like a plus, so you can't get it wrong. Cations are positive. Okay, so magnesium, Mg, generally will form, or actually always will form a 2+ charge. Now, if I have an atomic number, that atomic number is my identity. It's who I am, okay? I never ever can change the atomic number. So what's the atomic number of magnesium again? 12, because on the little box, you see magnesium, you see 12 on top. That's its identity. What is that also identifying?
The number of electrons.
Number of, no, specifically number of what? Protons. Specifically, it's the number of protons. If it's a neutral substance, you assume it's also the number of electrons. But in this case, it's not a neutral substance. It is a charged ion. It happens to have lost 2 electrons. Because when you lose electrons, you get more positive, right? Now your protons outweigh your electrons. They were equal. Now you've lost 2 electrons. You have overall a positive charge. So if originally it had, at a neutral state, had 12 protons, how many does it have now? Protons. Still has 12. Tell me how many electrons it has there. 10. You only are allowed to change electrons. You shall never change protons. Protons are its identity. If not, you change the actual substance, and you can't do that. We don't even know that much chemistry yet. Okay, so anions are going to only have a change of electrons as well, but they gain electrons. So oxygen, just straight up oxygen, O16, how many protons, how many electrons? 16 protons and assume 16 electrons, right. If I make oxygen as a negative charge, tell me its stats here.
16 protons, 18 electrons.
Good, 18 electrons, because it has a 2 negative charge, so it means its electrons outweigh its protons. You up 2 electrons. Okay, so we got protons and electrons kind of taken care of. You have a number of protons that's given to you on the periodic table. The electrons you assume are the same, or you look at the charge and figure it out from there. The neutrons are the last one to tackle, and it's all based off mass. So from oxygen, you know what? Maybe just a hair lied to you. Oxygen is number 8. My bad. I was thinking of mass. That is 10. Okay, got ahead of myself there. The mass of oxygen generally is 16 AMUs, or atomic mass units. If its mass is 16 and its atomic number is 8, what is its number of neutrons? 8. This one happens to be the same, because you're saying 16 mass minus 8 protons, 16 mass minus 8 protons equals 8 neutrons. So let's do the same thing let's do nitrogen. No, that's too easy. Let's do potassium. Okay. What is the atomic number of potassium? 19. What is the average atomic mass? 0.10. Okay, so let's just scooch that back. Let's just assume it's 39. So, what is the mass number again? Mass number? 39. What am I going to subtract to get the number of neutrons? 19. So subtract 19 to get 20, right? Protons and then mass. Yes. I'm going to talk about that in a second. Yeah, I did for a reason here. It's because it's closest, and that means I have a lot more of that particular isotope, but that's what I'm getting ready to get into. Okay. Let's do... Oh, this is a good example to know before I move on. So when we talk about isotopes, everybody probably knows the definition of isotope. It's like, I'm an atom with a different number of neutrons, but different from what? You know, like, what are you referring to? It's not really referring to anything except other isotopes. So every single atom in the world is an isotope. They're not different than atoms. They are atoms. So every atom is an isotope. They are one and the same. It's just atoms are not really specific. You're like, oh, I've got an atom of calcium. Well, that's cool, but like, how many neutrons do you have? How many protons? How many electrons? Isotopes just are a little bit more specific because they actually tell you more about is it calcium 40, is it calcium 41, is it calcium 39? It gives you more about its internal information. So hydrogen, this is hydrogen, this is hydrogen, this is hydrogen. If I say I have an atom of hydrogen, you're like, all right, that's cool. Which one? they're all hydrogen. But if I have an isotope of hydrogen 1, that's protium. That's just another name for it. If I say I have an isotope of hydrogen 2, that's deuterium, and then so forth, tritium. So these are just little names for that specific isotope, other than just me saying hydrogen 1, hydrogen 2, hydrogen 3. Those are another way of writing that same thing. So we need to know how to designate isotopes, because it's much more informative if you write out a couple numbers for me than just saying I have some nitrogen. So here are the two ways of writing isotope notations. Write this down, and then I'll scooch down and let you see the other one in a second. Am I going too fast?
Nope.
Gotta give me like some indications. I get excited very fast. So that is an isotope notation to know. This particular one is called the A to Z notation, or AZ notation. I really wish we could call it the Z to A. No, actually, no. It's called the A to Z notation for a reason. I want to call it the Z to A all the time. This top number here, what's the top number in the upper left indicating? The mass. Okay. So when it says A to Z notation, it is in order. A number. The bottom number is indicating what? The atomic number, right? Which is the Z number. I know you want to say the atomic number is the A number. The atomic mass is the A number. The proton number, which is its atomic number, is the Z number. So you have to know what these two numbers mean on the side of the isotope notation. The charge is always on the upper right-hand side. So this notation is called the A to Z notation. So if I ever say write it in the A to Z notation, I want like something like that. The charge can be there or it can't be there. I mean, it's okay for it to be there or not, because if it's got a charge, it's an ion. If it doesn't have a charge, it's just simply an atom. So this would be like, for example, 2+, and that would indicate the charge of calcium. So that's very informative. That gives you every detail about that particular isotope. The mass notation, this is just called the isotope mass notation. It's a lot simpler. It's just letter or atomic symbol dash mass. So this is uranium-238. So uranium-238's mass is what? 238. Do I have to tell you the atomic number of uranium? No. What am I always going to give you? This nice little paper in front of you. I will always give you the periodic table. It is a tool, okay? You don't have to memorize it. You just got to know how to use your tools, because if I give you a hammer and you don't know what to do with it, then we're never going to build a house together, right? So I'm going to give you a periodic table. You got to know how to use it. So if I say uranium-238, you tell me what is the atomic number of uranium. Uranium, it's towards the bottom.
92.
92. What's the mass of uranium-238? 238. So I can write mass notation as A to Z notation. I just have to look for that little piece of information I'm missing. Other than that, last question on this one, and before we do that big chart, is which of the numbers am I allowed to change? A number or Z number? Why the A number and not the Z number?
Because if you change the Z number, then you're changing.
Right. If you change the Z number, you change the identity of the thing. So if I put a 19 there instead of a 20, who is this now? Potassium. Okay. So you just change the entire identity. Well, that's not allowed. I don't have that kind of power. I can only change the number of neutrons in the substance. So if this is 20, I could say this is calcium-41. That just means it's still calcium, it's just got an extra neutron. So I can change the number of neutrons. That's the point here. Do not change the number of protons. So I can only change the mass number. Thumbs up if you're ready to go here. We're going to do a big chart. Okay. So this is on your paper. Yeah?
Yes.
I'm going to do like maybe 5 or 6 of different ones, so I'm going to bounce around and then let you guys finish it. And I'm going to start with some easier ones. So I'm going to start at the very top. And you guys are labeled. Yours is labeled, yes? Okay, good, because this is hard to see on mine. So you have your periodic table out. First thing you want to fill out is the atomic number. So what's hydrogen's atomic number? 1. This automatically tells you the number of what? Protons. So scooch over to the proton column, put a 1. So fill those out at the same time. Atomic number is proton number. Then I want you to look at the atomic mass given to you on that paper, on the periodic table for hydrogen. What is it? 1.008. That's not a full number. A lot of times they're roundable, but a lot of times our average atomic mass, which is on the paper, is a average of all the isotopes in the world, right? It's not a specific isotope. So I'm going to write that there for now, but then I'm going to say I need to round to the closest full isotope, which is this rounded would be just 1. So I'm putting the mass number as 1. And I'm showing you I'm getting it from there. But you'll realize that this hydrogen written here is different than this hydrogen written here. This one is like, hey, I'm hydrogen 2. There's no average. Don't even look at the periodic table. This one is a 2, so ignore that because you don't need to look at the periodic table. This one is just straight up 2. Do you see how this notation tells you the mass number and you just automatically write it? Whereas this one's like, hey, I don't know, let's look at the periodic table. Let's look at the periodic table and then round. It's just a little different. So I'm going to finish this first example first though. Okay, so if I know the mass number and I know the proton number, how do I figure out the neutron number? Subtract. 1 minus 1? 0. Perfect. Okay, what did I tell you to assume for the electrons if it's a neutral substance? Same as protons, so same as protons is 1. So it's just an analysis of information from one little piece of information given to you. So I'm going to skip the second row for now. I'm going to go down to H2 because I started there. So automatically, what can you look at? The atomic number. So you know it's a 1. Atomic number is 1. What automatically do you fill out from there? Proton number is also 1. Okay. Is it charged? No. So it's neutral. So what else do you automatically know? Say again? Electrons. I heard some people say neutrons. If it's neutral, it doesn't tell you anything about neutrons at all. I know neutral and neutrons sound similar, but if it's neutral, it means protons and electrons are equal. So I already know my number of electrons is also 1. All right, so I'm going to bounce back to the mass here. So this is an isotope notation of the mass notation type, so it's -2. That 2 means the mass is 2. Don't even need to look at the PTOE. If that mass is 2, the protons are 1. How many neutrons do you have? 1, because you did 2 minus 1 is 1. So I set this up like that so you could just subtract right there in your head. Let's go ahead and do, well no, we'll come back down here. Let's go to this calcium one right here, calcium 2+. Calcium 2+. What's the first thing you want to find? Atomic number is what? 20. What else do you know then? Is that this column? Protons is 20. Okay. What else do you almost know? Just simply by looking at this. Is it neutral? No, it's charged, right? So what happened? Lost 2 electrons, right? So if originally they were both 20 protons, 20 electrons because it was neutral, and then I lost 2 electrons, what's the new number over here? 18 electrons. Just because this charge here means I've lost 2 electrons, so I need to subtract them from what it originally was, which was neutral. Okay, so I don't know the average atomic mass. Where do I look? Okay, what is it? 0.0 what? 08. Okay, that's not a full isotope. That's an average of all the isotopes, so we're going to round that to what?
40.
Simply 40. 40 minus 20, so mass minus protons gives me 20 neutrons. Who's feeling this? Like you see the math here. All right, I got a couple. I need to get it on board here. Let's do beryllium here, right underneath it. Beryllium. This one's got a lot of information. We probably don't even have to look at the periodic table. Beryllium has what atomic number? 9 or 4? 4. Remember the A number, A to Z. Z number is down here. That's the atomic number. Okay, 4 also tells us the what? Protons. Is this charged? No, what else do you know then? Electrons. Protons and electrons are equal because it's not charged. It's not an ion. So this is also 4 electrons because they cancel each other out in terms of charges. All right, what does that 9 tell us? Is it the atomic mass or the mass number? Mass number. Like that's what this is. A number is mass number. So for a little exclude this atomic mass because we don't need to look at the periodic table. So we know the mass is 9. If the mass is 9 and the protons are 4, how many neutrons? 5, because 5 and 4 make 9. Those are the only 2 subatomic particles that have mass. Electrons are so negligible, they're itty bitty. Did I share my fun fact about the internet with you yesterday? That's like, I don't know, I'm here. The entire internet is made up of tons and tons and tons, millions, trillions of electrons, right? It's just electricity. Electricity is just simply electrons moving to and fro, giving us information in like a little binary code and throwing at us in different images because computers know how to process that stuff. I don't. The entire internet weighs as much as a strawberry does. And that's it. That's it. That's how small electrons are. They're just so small. All the internet is compressed in a strawberry. It's like 16 grams or something like that. Crazy. Okay, fun fact for the day. All right, let's do another charged one. Let's do up here. 16 and 8, oxygen 2 minus. What automatically do I know? I know first the atomic number, right, is 8, because that's what the 8 down here number is. And then you know from that what? Protons and... Oh, hold up. Before we get there, give me charge. Tell me what the charge indicates to us. Good. 2 negative charge means that you've had 2 extra electrons, because electrons are negatively charged, added to the system. So originally they were 8 and 8. Now what am I? 8 and 10. Oops, I'm up at 18. 8 and 10 electrons, because there's 2 more, because that gives it the 2 negative charge. All right, go back over here. What's the 16 telling us? So information for the atomic mass is not needed. The mass number is automatically 16. Tell me what the neutrons are. They happen to be 8, because 16 minus 8 is 8. All right, let's do one that's like really, really nil on the whole information. Magnesium. We're given nothing. So what do you have to consider? Or what do you have to consult? PTOE. What's the atomic number? Yeah, first one. 12. Okay. What else do you know? Okay. And what else? Because not charges. Neutral means protons and electrons are equal. All right. Now what are you consulting on the periodic table? Atomic mass is what on the periodic table? 3,1. We're going to round that to what? 24. Okay, so 24 minus 12 is 12. You guys are geniuses. Okay, good. Tell me one more you want me to do, based off the list of things that we've not done. P, okay, perfect. So phosphorus, 3215, P, 3 minus. Give me atomic number. 15. What else do you know? Protons, 15. What else do you almost know? You just got the little finagling here. How many electrons? Did I lose or gain electrons? Let's talk about that first. Gain, because they gave me a 3 negative charge. So 15, now I'm at what? 18 electrons. Mass number? 32. Do I need this atomic mass one? Nope, I already know it. It's 32. What's 32 minus 15? 17 neutrons. Okay. Take a couple minutes to work with your partner on a couple more of those, just so you can do it by yourself. You can start checking yourself. I'm doing those in red if you need to. Jack, what's 238 minus 92? 146. Thank you. Yes. Oh, I'm sorry. I looked quickly and I thought it was a ion. I thought I gave you an ion on that one. I actually just didn't look. I was trying to from memory. I'm sorry. Electrons. Take one more minute. Good, sorry. I was doing different order. Oh, really? Alright, I'm videoing and I'll put this up if you need me to later. I'm going to give you a couple more seconds to ask me questions. We'll move on to one more calculation. Okie dokie. And scroll this way. I didn't do that one. I'll do it. Good. All right, let me talk to you about average atomic mass. It's a quick calculation. I'll do one or two examples, and then you guys are going to start your lab. And the lab is very simple. It's practicing this average atomic mass technique. So, before we move on, tell me what relative means again, like relative abundance, for example. Relative. It's not a calculation. It's more of a, okay. Compare. Okay, it's a comparison. Relatively, who's taller? Okay. Me? Okay. So relative, it's a comparison. It's not a number. Now, relative abundance, though, is we can calculate something from that. So we actually do morph it into a number. It just takes a little bit of math behind it. So do not write this part down. I'm just going to give you a quick comparison. So there's there's water and water indicated here. Each of this hydrogen, hydrogen, oxygen, they have masses, just like we said earlier. Hydrogen generally has a 1 mass. Oxygen generally has a 16 mass. But there are such things as oxygen 18. There's very, 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 very few of them, though. But we sometimes need a number, so we actually add it and make it into a percent. So we morph it into a percent. So there's a lot of the waters that are hydrogen 1, oxygen 16. There's very few with this 18 number here. But there's that, as you can see, 99.8% of all water molecules look like that. Only 0.2% of them look like this. So that's where our relative abundance comes in. Every relative abundance we can morph into a percent, and all percents always add up to what? 100, okay? So we have to give them a number for our calculation purposes. So what you do is need to know, you need to know that we have to use percent abundance, not relative abundance. We have to use percent abundance to get average atomic mass, and that's a calculation we're going to do together here in just a second. These averages are not like math class, okay? They're not like math class averages where you like add everything up and divide by the number that you added. Like if I added up all your heights and divided, I have to divide by like 30, right? Not like that. We have to use percents, and I'll show you how to do that. And every time we calculate an average atomic mass, you actually, if you know what the substance is, you can look on the periodic table and see if you're right. Because all periodic tables it's an average of all the isotopes in the world. So that is what the value is on the periodic table. It's called the average atomic mass. Okay, let's do some calculations with this. Okay, so I'm going to give you data. Sometimes I'll give you data that you can calculate percentages from, but I'm actually giving you the percentages right here. I'm giving you percent abundance. In this case, I have two different isotopes of chlorine. I have chlorine 35, and I have chlorine 37. If I tell you that I have two isotopes, I'm probably going to give you their exact weight. And now you'll notice their exact weights are not exactly 35 and 37, but that's where we have that rounded number there. And I give you their percent abundances. So what you need to do is 1 multiply percent as a decimal by the mass. And when I say as a decimal, what is that as a decimal? You move the decimal back twice, right? Because it's like a percent is already multiplied by 100, so you're essentially dividing by 100. So 0.7577, right? And this is what? Okay. So first thing we're doing is multiplying the percents by their mass, by the masses of the isotopes, and then we're just going to add them up. That's it. No third step of like, hey, let's divide by 2. None of that nonsense. So we're going to take this point. Will you guys pull out a calculator for me, somebody? Take that first percent. Multiply it by 34.968852. Extremely accurate. 68852. And these are atomic mass units, by the way. AMU, that's a unit I've not spoken of yet, but AMU is a unit that you want to know. Atomic mass units. Okay, what'd you guys get for this first one?
26.495899916.
I'm just gonna stop there. Okay. You can stop after a couple decimals, but you don't want to round too soon. If not, you will have rounding error. All right, so that's the first isotope. The second isotope, same story, different numbers. 0.2423 multiplied by its mass of 36.965903 AMUs. And whenever you guys get there, let me know. 8.95683. AMUs. Okay. So we've done the whole multiplication. What did I say next step was? Add. Boom. Add those two numbers for me. I'm hoping it's 35.453. Okay. Yay. Hopefully we're really close there. Okay. 453 AMU. Okay. And look at chlorine's atomic mass on the periodic table. What is it?
35.45.
Perfect. See how we just verified? We actually were correct. So the relative abundances of chlorine, whenever you take their percents and you account for the masses that they make up of the entire sample of isotopes across the world of chlorines, and then you add them up, it will equal what's on the PTOE. And that's how, if you know the element, you can double check that you are correct. Okay? Yes.
I'm sorry, what did we just find by doing all that?
The average atomic mass of the isotopes of chlorine. Because each individual isotope has its own mass. It's 35 or it's 37. But apparently, who's more abundant here? Which type of isotope? Isotope chlorine or isotope chlorine 35 or chlorine 37? 35 is so much more abundant than the other one. So it's like a weighted average. It pulls the average closer to 35 or 37. It pulls it closer to 35 because look, the average of all those chlorine isotopes is 35.45. So the more abundant one pulls the average closer to itself. So if I told you, and I already, that previous example, I told you there were such things as oxygen 16 and oxygen 18. Which one is more abundant? How do you know? I know I told you that, but how would you know from the periodic table? What is the average atomic mass in the periodic table for oxygen? 16, right? So, like I said, this one's probably like 99% relative abundant, and this one's like 1%, because the average of oxygen's atomic mass is so close to 16, that's got to be super high. So the higher percentage one kind of controls the average more. So tell me one more. Tell me for fluorine, what are 2 different isotopes of fluorine you think I have? Or that are out there? Fluorine. Fluorine 19 and fluorine what? Sure, let's go with fluorine 20. Maybe there's a fluorine 18, I don't know. But who's most abundant? Because the average is what? 19.00 AMU, right? So there might be like 0.5% of this one and like 0.5% of this one and then 99% of this one because it's controlling the average. Okay, cool. That was a good question, so I actually need to talk about that. Okay, so isotope lab. Okay, isotope lab is called Benium. Benium comes in 4 varieties. Pentobean Benium, Lenobean Benium, kidney bean Benium, and something else, black-eyed pea Benium. Okay, those are the 4 isotopes of Benium. You have to separate them out, account for their relative abundances, mass them, and then calculate the average atomic mass of each. This will take you about 30 minutes. Fantastic. We have 37 minutes in class. Okay? So, I'll let you guys choose your lab groups. 3 people per lab group. Go. 3 people per lab group. This is a nice lab table for 3 people.
No, it's fine. We'll count it later because we're kind of just wrapping
When Bella will join y'all's group on our next slide, okay? Just remember that. Okay, darling.